Okay, can everybody see my presentation? Very good. So, as you all know, my name is Julius Oeff, and right now, as I got introduced, I'm working at the BAM. I'm developing an NFC sensor system, which will be embedded in concrete in the future, and it will get powered through the wall so the sensor readings can be read out. And my main hobbies are to develop tiny devices and measurement devices for all kinds of um, scientific measurements. So I still have a question to all the participants. I would like to know what kind of sensors you are working with, and um, yeah, what kind of measurements are you focused on? So I might,
Ultrasonic guided waves for me.
yeah. So it's a time-based measurement system for, and you want to have accurate measurements and signals you want to analyze.
Yes, it's time-based.
Okay. So first of all, so I try to include the ultrasonic time-based measurements later. And my outline would be the introduction to measurement electronics, the understanding of multimeters, oscilloscopes, and analog digital converters, overall signal chains and measurements, and also the sources and mitigations of electrical noises if they appear, and also some fundamentals of electronic magnetic compatibility. Um, and furthermore, I want to talk a bit about about the designing of measurement setups itself, also the electromagnetic compliance, um, and what influences could appear in the daily measurement setups. Also, in the end, I want to talk about some problems I encountered in the past, and what I have found, or how I found the sources of the noises and the disturbances I had in my setups. So I will be really fundamental and basic, and I'm guaranteed that you know about multimeters or oscilloscopes, but I will include them in my talk too. So the introduction to measurement electronics. I'm sorry. Um, as I said, it will be fundamental. I would talk overall, or yeah, I want to talk about the key components, which are at first of all the transducers or the sensors which pick up the signal. Then then I want to show some examples of data acquisition systems and some and what signal conditioners are. The sensors itself, they respond to any kind of physical input, and they can, yeah, convert your physical signal into electronical signals. And besides that, there are transducers which convert one form of energy to another, like temperature, pressure, light, radiation, and sound. And after that, there will be a sensor which pick up the transduced input and yeah, convert them again to the electrical signal. So quite the data acquisition systems, I included one analog non-electric data acquisition system, which would be the Campo Strokes recorder on the top right, which burns the sunlight onto a piece of cardboard, which is absolutely non-electric, and but it's still a data acquisition system. And besides that, more modern, yeah, or analog electric multimeters or some seismometers, which plot the information on also on a piece of paper, and you can acquire the data you wanted to have without digital converting. More modern multimeters are purely digital and will show you the voltage of a given signal. Also, the signal conditioners would be necessarily if you have tiny signals and really small amplitude signals in measurements. For instance, the ultrasonic pulses you pick up, they might be really small and you have to amplify them. The signal ultrasonic transducer as a receiver is a single-ended signal, so you only have one output, and for that you could use a single-ended operation amplifier. It would be the the top right one, and also the differential op amp could be used if you have a differential output. And the last one I included is the transimpedance converter. It's also an operational amplifier, which converts tiny currents into voltages. This is only a overview. I will go a bit deeper a bit later on those. So understanding the multimeters, oscilloscopes, and analog digital converters would be the basic I want to give you at this point. The multimeters are converting electrical values into readable numbers, essential for troubleshooting. They are really slow. They read one measurement per second, maybe a bit faster. Could be possible with modern multimeters, but they cannot display the signal form and they cannot store the values you want to acquire in your measurement setup. The oscilloscopes, I bet you all have used them too. They can acquire the signal forms up to very high frequencies. You can take a snapshot, but the long-term data acquisition would be a challenge. It is possible. There's the interface to connect them via Ethernet and to read them out over with a different computer, but not continuously. For the continuous case, I want to talk about the analog digital converters and what parameters they have. The analog digital converters have the sample rate, the maximum samples they can pick up per second. Also, they have the limiting factor of those would be the input voltage range and also the resolution they convert the analog voltages. For example, the 12-bit analog digital converter with an input range from 0 to 5 volts would have a resolution of 5 volts divided by 2 to the power of 12. That would be 1.22 millivolts per bit. And that's the maximum resolution you would get out of those analog digital converters. I like them especially because you have to think about the sample rate, about your signal, about the highest frequency you want to pick up, and also about the input range. So you have to think about every parameter you're gonna use the analog digital converter. In a special example, or it's not a special example, it's a basic analog digital converter. It's called ADS1118. It has a changeable input range from 0 to 2 volts or up to 5.5 volts. It has 4 channels, and the sample rate is only 860 samples per second, which means you would have the possibility of acquiring the highest frequency of 430 hertz by the Nyquist theorem. The bit depth is a bit better than the 12-bit. It has 16 bits. So you see on the bottom left the resolution of the smallest bit you can acquire with that analog digital. So overall, I want to talk about also about the signal change in measurement electronics, which would be the main topic.
Sorry, Geoff.
Yes.
Can I ask you a question?
Yes, please.
Can you go back of a couple of slides?
Yes.
I didn't understand. So here it's 12-bit, so that's why it's 2 to the power of 12. And
yes.
The following one is 16-bit, so we have a slightly more bit depth that gives you more samples per second.
It's the bit depth is not the samples per second. It's the dynamic you can input into one of those samples you record. So,
okay.
So the input range, let's compare them. If the second one would have a maximum input range of 5 volts, like this one, this one is 12-bit in the bit depth. The tiniest resolution would be bigger than the one of the 16-bit analog digital converter. So we see we have 1.22 millivolts per bit at 5 volts, and the 16-bit depth of this analog digital converter is way smaller. We have at 5.5 volts maximum input range, we have 84 microvolts per bit. So that's the resolution.
It's the order of magnitude less.
It's more fine and you can see more details.
Okay, thank you.
Okay. And also it would be embedded systems question. You have that analog digital converter and you have an interface. You have to connect to that chip and you have to read it out via special drivers in being read out by a microcontroller, for example. So it's not a device you plug in your computer, but you still have to use a microcontroller to talk to this analog digital converter. And this microcomputer could be plugged into a USB port, and then you can transfer the readings of that analog digital converter. And this interface is SPI. It's called SPI. There are a few interfaces in the embedded systems world. And the SPI would be one. And this is a quite slow analog digital converter. So there are way faster ones, like the oscilloscopes going up to a few megahertz, a few hundred megahertz. So the signal chain itself is, I would see it as following. You have a source of any kind, and you have a transducer converting the energy from one form into another, and then a sensor would pick up that converted energy. In case you have to amplify it or gain the signal, you have to use one of those amplifiers. And if you have a disturbance, like low frequency noise in ultrasonic sensors, for example, you mostly would use a high pass filter so you can cancel out the low frequencies. After that, you will go into the analog digital converter, which is connected in the one or other kind to the computer or to a data acquisition system. And that would save the samples and the signal form into a bit stream or some kind of digital file. So as I said, sometimes the signals have frequency components you don't want to include into your measurements because they're not important. And for that, you would use, in this case, what I'm showing you here is the signal conditioner would be a filter, and you would only look at the shown peak, the second highest peak, which might be interesting, and then the photo would be a band pass, and you can only let this band pass to the analog converter, so you only get the frequencies and signals you want to acquire. And yeah, overall questions I ask myself is when I want to measure something, does my signal, is it big enough? Does it need amplification, or does it have frequency components which I don't want to have in my measurement? Do I need a filter? Is my measurement time or frequency sensitive? And if it's, for example, time sensitive, and you want to measure the travel time of an ultrasonic wave, you would have to use a high frequency ADC converter or the analog digital converter, and to get the proper timing of your signal, which would arrive. In the other case, the frequency sensitive measurements would show in a fast Fourier transformation or in the result of a FFT. And yeah, besides that, what I talked about already is the sample rate and the dynamic range. How big is your signal? You cannot acquire a 10-volt signal or signal form which would peak at the maximum input range of the analog converter. You would saturate the input, and you cannot do anything with the measured values. So what should we do when we encounter higher noise levels in our measurements? This is the following upcoming topic. We want to have a high ratio, signal to noise ratio. The noise should be as small as possible. The signal should be as high, as big as possible, but lower as the input range of the system which is acquiring the signal. Noises can be differently shaped. It could be a static noise in the background. It could have a shape. It could be periodically, and in either way, it could be it could result in a bad measurement, which is hard to analyze. And what I try to ask myself is, what is the cause of the noise itself? What disturbs my measurement? Which is not always an easy task, because if you have a high noise, you might have no idea where it's from. So there are different kinds of coupling methods, not the methods, but causes of noises. And in the first case, it could be inductive coupling, which would look like the bottom right picture. If you have twisted wires, not twisted wires, but badly organized cables. They can crosstalk. You can have one signal on the one line. It might jump over to the other line, and you would have a signal at a place you don't want to have it. Also, a side effect of high voltage lines, if you have ultrasonic transducers, they might get driven by high voltages, like 150 volts, and you have pulses on them. You might have seen the pulse appearing on a different line, which would be the capacitive coupling on the bottom left. And it's like a big capacitor, or the signal lines would act as a capacitor, and you would have the electrical field would induce a signal on the different signal line. Also, again, that's why I included the operational amplifiers, and they would, in detail, I want to talk about the single-ended and differential operational amplifier. And I'm trying to show you methods to raise the signal to noise ratio. So if we have some coupling effects on our signal lines before the signal conditioner, the signal would where the noise will get amplified too. And this is the worst case you could have. We have here a inverted operational amplifier with a gain factor of X. So I didn't wrote any numbers here. And you can see the coupling in the middle and the amplified signal or coupled noise. It's not a noise, but it's a peak. It will get amplified too. So what could be, one method of suppressing that inductive or capacitive coupling would be a grounding, a shielded wire, a quartz cable, and it's suppressing the coupling effect, because the inductive coupling effect will get routed to the ground, and the noise is a bit more silent, and it will get a bit less amplified. A twisted pair cable can be used to transport a signal, which would be positive on the one cable and negative on or inverted on the other cable. And if something couples into both cables at once, then the differential operational amp will add both signals, and because the coupling effect will have the same effect on both cables, the impulse itself would get suppressed and subtracted of this operational amplifier, which is differential. The even better way would be a shielded twisted cable. It is the non plus ultra, but you don't always have the possibility to have the signal coming on two cables. So,
excuse me, I have
yes,
one question.
please.
The amplifier also will introduce some noise. How do you deal with it?
Exactly. So amplifiers, if you have a high gain, you have, or the amplifier itself would have a noise which is included if you have a high gain. And there are different kinds of amplifiers, and the range in which you amplify, like if you, it's a question I have to think about a bit. You shouldn't max out the amplification factor. So if you have a operation amp, you want to tune it to 1,000, the noise in front in the signal lane will get amplified too. But the noise of the op amp itself, I have to think about it. I might have an answer in the end of the presentation. Maybe you can remind me. And
Okay, thank you.
All right. So the fundamentals of electromagnetic compatibility is you try to, or the definition of emission control is the limiting the amount of electromagnetic energy that your device emits. And also the opposite of that would be the immunity, and you will try to shield your device. And yeah, so it doesn't capture, or it doesn't get some coupling effects of high voltages or capacitive coupling. The grounding and shielding is the most important part against those problems. And yeah, will have to have the metal case in the best case of your device, which is connected to the ground of the power supply. And there are many more methods, but they all include the shielding being connected to a proper ground to block all those interferences. In detail, the limiting amount of the electromagnetic energy that the device emits is part of the emission control, as I said already. And the most important thing about this is reducing the emission to interfere with other electronic devices. And also you have to be inside some standards you are trying to, you have to be in those standards. Again, the immunity is the same idea as shielding your cables. And the devices have countless signal lanes included inside of the device. Mostly they're digital, but a few of them are analog, and they are really sensitive to any kind of the electronic magnetic interferences. As I said, the grounding is the most important, and the connections of the grounding points internally of a device, which connects all the modules and the different signals. They just have to have a nice connection, which in best case should be soldered, so the resistance is really low and you don't have the interferences get swallowed by the grounding, shielding, and yeah, I'm sorry, I'm a bit nervous. So if you want, we could have a 5-minute break. What do you think?
Okay.
Okay.
All right. Then I will be back in 5 minutes.
Okay.
All right, thank you. Okay, is everybody back?
Okay.
I would be ready to continue. Okay, so the next point would be designing a measurement setup and designing electronics for electromagnetic compliance. It's quite similar and to the chapter before. So I will talk about minimizing loop areas. I will tell you in a moment what that is. Keep the loop areas of a signal or a power line as small as possible. Use a proper shielding and grounding, something you have heard before. Implement the effective shielding and grounding techniques. Filter the power or signal lanes. The usage of different filters to get rid of unwanted frequencies or noises. So in designing PCBs or printed circuit boards for electronics, you would run into troubles if you have a loop, like a ground loop or a voltage line loop, which is an electronic connection which runs in circles. It would act as an antenna, and which which is picking up the electromagnetic interferences even better. And to avoid them, don't build loops in your PCBs or in your electronics. In the other case where you might have experienced something similar would be an audio system where the audio emitters, the studio monitors, for example, would plugged in a different power socket than your computer. Then you will hear a humming sound, which would be the frequency of the main power line. And to avoid this big ground loop, you should use one power socket. The same would apply to measurement electronics. If you use different kinds of measurement devices, which are plugged in different power sockets, and they are connected with some signal lanes, and the ground would connect both sides, you might pick up the same mains voltage frequency of 50 hertz. So yeah, try to avoid it, or think about what I said if you encounter that 50 hertz signal in your measurement. Also, again, the proper shielding is always important. It's blocking the electromagnetic interferences, or it would affect your circuit and your design, your electrical design. Where it's getting really important is high frequency electronics or high frequency signals at over, let's say, 1 megahertz. A lot of electronics and measurement devices will have shielded modules, and so the low noise, or the amplifiers, which could be low noise amplifiers, pick up even less noise from the background. We also have power line filters, which I will show you two of them. The 50 hertz frequency is one part you don't want to have included in your signal lanes. But if you have many devices in a department, for example, many of them might emit on the power line itself some noise, which can be picked up by your measurement electronics. The most oscilloscopes and more expensive measurement devices already have filters included. But if you use some old analog oscilloscope, for example, you might pick up even more of those noises. And one filter would be a main power filter. They have some inductors and some transformers, and also some capacitors to suppress higher frequencies. This would be one which suppresses the frequencies between 100 kilohertz up to 100 megahertz. And it could be an option if you have noisy measurements. The second method would be an isolation transformator, which is mostly a transformator which has the winding ratio of 1:1. So you input 230 volts and you get 230 volts on the other side. But it's isolating it's a galvanic isolation. And it should reduce your electric noise significantly. Also, the ground loop is eliminated by that. And those are a lot of methods to suppress your noises or to gain your signal-to-noise ratio. In the first place, those methods I showed you, the most of them are hard to include as a scientist, because you have a given setup and you not always have an isolation transformer or a power line filter, which would be the electrical people or people who install the setup. They could think about it before. So mostly the only options are filters, high pass filters, low pass filters, and band pass filters, which could save your signals, and it would be the first try and the first option probably. So now I'm almost done, but I had some experiences in the past in the one solar power device I have built a few years ago in a research project. And in this device, there is a tiny chip which measures the current which goes through the main power line. And on this tiny chip, it converts the current into voltage. And on that voltage line, on that signal lane, I have found some switching noise, which is shown by the red arrows on the right side. That's the signal shape of a switching noise, for example. And the only candidates of emitting that noise or that kind of noise would be number one on the left side, the picture. I included in my design a step-up converter, which converts a DC voltage to a higher DC voltage, in this case 5 volts to 20 volts, and also the power supply unit, the number 2, which also was working with the power switch inside of it. So I was measuring with the EMI, with the electromagnetic interference probe, different places of, different modules of my design. And in the end, I could isolate the switching frequency in the power supply unit. It's shown with the green arrow. And I could see the exact same frequency which I had in my current sensor. In the end of the day, I couldn't filter that signal. I was living with it, and I made a firmware or software update so it could handle that kind of noise. Sadly, I didn't have too much time to eliminate it completely. And if nothing helps, and if you have just a noisy signal, here we have a synthetic generated signal. It's a periodic signal which is overlaid with the Gaussian noise, and you have a signal to noise ratio way below 1. But in this case, because the signal we are searching for is periodic, we can do a fast Fourier transformation, and we see the big amplitude at on the left side of the fast Fourier spectrum. And in which case this could be useful is a different question, but the signal which is way below, the signal to noise ratio, which is way below 1, is still usable. So a post-processing of a noisy signal can save your day. So that was my tiny presentation about measurement electronics and the influence of noise and some methods of getting rid of that noise you have in your measurement devices.
Okay, thank you very much, Julius. Maybe we have some questions or comments.